It's Chapter 12, Matrices. 12.4, Part 2. I'm Augustus, and I'm Austin, and we are Civil War reenactors. And today, we're going to reenact for you... Oh, sorry. Solving a square system. Alright, so remember in the last section, the last set of notes, we had a square system, which was x minus y plus z equals 0, 2x plus y minus 3z equals 7, and 3x minus 2y equals negative 4. Yes, I do recall, and this is a square system because it has 1, 2, 3 equations and 1, 2, 3 variables. Very good. Austin or Augustus, whichever one you are. I am Augustus. All right, sorry. All right, so what we're going to do is think about this system as actually two matrices. Now, way back in 12.2, we would solve this system by making an augmented matrix that held all the coefficients and all the constants. And then we would find the RREF of that matrix, and that would be our solution. This is a different way that we're going to go about solving this with matrices, with the different types of matrices. And this strategy that we're going to see right here is only for square systems. And it only works in certain cases, so I'll talk about that. But the cases where it doesn't work, we're going to have to fall back on the augmented matrix and the RREF. All right, so I'm going to take you through a process that's going to show you how we're going to find the solution, and you don't have to do all these steps every time, just so you can see where the solution comes from. All right, so we're going to make two 3x1 matrices, and they're going to be equal because they're going to take the left side of the equations equals the right side equations. So this matrix is going to hold the left side expressions, x minus y plus z, 2x plus y minus 3z, and 3x minus 2y plus 0z, I guess we consider that, equals 0, 7, and negative 4. Right? And these two matrices are equal because of what the system says. Now we're going to call this one is called the constants matrix because it is the matrix holding the constants of the equations. This side is holding the expressions, and we can actually think of this matrix as the product of two other matrices. One matrix that's just the coefficients, the coefficient matrix, so 1, negative 1, 1, 2, 1, negative 3, 3, negative 2, 0. And this one that holds the solutions, for right now, they're just called x, y, and z. And that will equal the constants matrix. All right, so this is the constants matrix. This is the coefficients matrix that we're familiar with. And we can think of this as the variables or solutions matrix. And what we know is if we did matrix multiplication using, the process for matrix multiplication, it would be 1 times x plus negative 1 times y plus 1 times z. And that would give us that entry. 2 times x plus 1 times y plus negative 3 times z would give us that entry. And then 3x minus 2y plus 0z would give us that entry. So the product of these two matrices actually equals that matrix. So this one times this one equals that one. So what we really have is the coefficient matrix, which we'll call A, times the variables solution matrix, which we'll call X, and that equals our constants matrix, which we'll call B. So that's the coefficient matrix, solutions matrix, and constants matrix. And if I can solve this matrix equation for this matrix, I have my solutions. Well, how do I solve this equation? How do I get x by itself? Well, I know. If you want to get x by itself, it seems to me you should get rid of the multiplication by A. Well, how do we do that? Well, I don't know. I thought you guys were Civil War reenactors. Oh, we are. All right, well, let me tell you. How do we get rid of this multiplication by A? Well, we would multiply by the inverse of A. So if I do A inverse times A times X, and then I would have to do the same thing on this side, A inverse times B. If I multiply on one side of the equation, I have to do the same thing on the other. These two will become the identity matrix. And we know the identity matrix times any matrix is just that matrix. So there is our solution. The solution matrix is equal to the product of the inverse of A times B. And there's our solution. Now, a couple things to note here. This is only going to work if A is square and A has an inverse. And then the other thing that's really important is that, remember, matrix multiplication is not commutative. So if I multiply A inverse on this side, I have to, on the left side of this equation, of this expression, I have to multiply it on this side as well. So it has to be in this order. You can't do B times A inverse. It has to be A inverse times B. So this is going to be our solution. All right, so we're just going to get our solution by doing, again, the inverse of the constants, of the coefficient, and times the constants. Right, inverse of coefficient matrix times the constants matrix, and that will give us our solution. So let's see that happen on the calculator. All right, so you guys remember how to use the calculator? I sure do. All right, first, turn it on. All right, I think we still have that matrix A in there from last video. So there it is, the 1, -1, 1, etc. And then I think, so that's what the first thing you want to do is set up matrix A. Then the next thing you want to do is check your determinant really quick. So you don't want to go through this process unless it actually has an inverse. So really quick, we'll quit out of here and we'll do matrix math determinant A. And remember from last time, it wasn't 0, so we're good to go. If this was 0, A wouldn't have an inverse, and we would have to go back to the augmented matrix and the RREF, which is not a terrible thing. I'm not sure this is even better anyway, but we need to know how to do this. All right, so now I'm going to do matrix A inverse. Remember, I get the inverse by doing just the matrix with the inverse symbol, and then times matrix B. And there is my solution. X is 5.5, Y is 10.25, and Z is 4.75. So all we really have to do is, like I said, you don't have to do all this work here. Just once you have your system, go straight to this step, get your coefficient matrix and your constants matrix, enter this as A, this is B, check your determinant of A, make sure it's not 0, and then do A inverse times B. All right? That sounds delightful.